if you are subjecting a member to tension or compression, then then what you need to do is look for a material which has got the smallest value of rho by E. If you are looking at a beam which is being subjected to bending, whether it is in a simply supported condition or a cantilever beam condition, then what you need to be minimizing among the materials is rho by square root of E. And for a panel or a shell, what you need to be looking for is a material with lowest value of rho by cube root of E. Now, on the other hand, if you are selecting a member uh, based on the constraint that the member must not undergo permanent deformation when subjected to the loading in the problem, and with this constraint, if you want to select a material with lowest amount of mass, then if the member is being subjected to tension or compression, then what you need to be looking for is a material with minimum value of rho by the sigma y, where sigma y is the yield strength of the material, rho is the density of the material. If you have a beam which is being subjected to bending, then you should be looking for a material with a small value of rho by sigma y to the power 2 by 3, and for a panel you need to be looking at member with smallest value of rho by square root of sigma y. Now for a specific example of steel versus aluminium based on stiffness requirement, we had seen that if the member is subjected to tension or compression, then whether it is a steel alloy or an aluminium alloy, both of them would have the same mass. Now, on the other hand, if it is a beam or a panel which is subjected to bending, then in that particular case, you would have aluminium as a better choice when weight reduction is your motive. So, when aluminium is chosen over steel, we had seen that the weight of the member for aluminium alloy would be about 40% smaller than that for the steel alloys. Now, this was for one specific example, and there are huge number of materials to choose from. So you need a better way to analyze things. So, all right, let us see how this can be done. There is a professor from Cambridge University by the name Ashby. Okay, by the name Ashby, who has come up with an ingenious way of representing the data so that the choice of the material is more intuitive. So he has made a huge number of charts. We'll go through them, go through some of them. So now this is an Ashby chart for thermal conductivity of metals, ceramics, and polymers. Now, please pay close attention to the numbers. So, what is the unit of thermal conductivity? What is the unit of thermal conductivity? Are you able to listen? Hear me?
Watt per meter Kelvin.
Yes, sir. Watt per
It
meter.
is watt per meter Kelvin. Okay, so the SI unit is watt per meter Kelvin. Now, let us look at thermal conductivity of some of the commonly used materials. Okay, so amongst the metals, what is the highest thermal conductivity that you can get? What is the
400.
highest thermal conductivity that you can get? So you can get
400.
highest thermal conductivity for copper, and amongst the, well, for pure copper you can get a thermal conductivity of close to, how much is this? This is around
500.
no 400, 100, 200, 300, 400. Okay, so it has a thermal conductivity of about 400. what is the thermal conductivity, that the maximum thermal conductivity you can get for aluminium? For aluminium, you can get somewhere around 250 watt per meter Kelvin. So amongst the metals, copper and aluminium give you high thermal conductivity. Where is our hero steel? Steel is here. Okay, so carbon steels are giving you thermal conductivity of how much? 20, 30, 40, 50. Okay, so this is about 50. And so you can see over here that stainless steel, what is the value that you're getting for stainless steel? So for stainless steel, we have about 15. And which metal has got the lowest thermal conductivity amongst the metals? Titanium alloys have got the lowest thermal conductivity amongst the metals. How much do they have? So titanium alloys, depending on what you're dealing with, you have 2, 3, 4, 5, 6, 7. About 7 watt per meter Kelvin. Okay. Remember that the y-axis is a logarithmic scale. So even though they appear to be close by, they're actually not close by. So if you look at thermal conductivity of titanium, okay, it is about 50 times 50 times smaller than that of copper. So it has very low thermal conductivity, and this has implications. Okay, so can you name some particular problems that you face while handling titanium because of this very low thermal conductivity?
Thermal stress.
Yes, you would be dealing with very high thermal stresses because well, you would end up with very strong thermal gradients. So machinability of titanium is a big problem, and one of the reasons is this low thermal conductivity resulting in some serrated chip formation. Now, so next class of alloys that we can next class of materials we can look at are ceramics and glasses. Okay, now ceramics and glasses, we can look at ceramics and glasses. Now, intuitively, you would feel that ceramics would have lower thermal conductivity as compared to metals. But there is a big surprise. What do you see? You see that if you look at the thermal conductivity of something like silicon carbide, okay? So the silicon carbide, even the average thermal conductivity that you get for silicon carbide is of the order of 150 watt per meter Kelvin. So it is higher than it is higher than most of the metals. Okay, and aluminum nitride can also give you a high thermal conductivity. Boron carbide also has good thermal conductivity. And amongst all the metals, even if you look at the lowest one, which is the silicon nitride, okay, even that is not too bad. Okay, so this is about 18 watt per, sorry, not 18, this is about 25 watt per meter Kelvin. Okay, it is even higher than that of stainless steel. So fully densified ceramics do have uh, reasonably good thermal conductivity. And what about polymers? So next, if you go to polymers, polymers have got a pretty low thermal conductivity. Almost all of them, all of them have got a thermal conductivity of, what do you have? So all of these guys over here, they have a thermal conductivity of less than 1 watt per meter Kelvin, depending on what you're dealing with. So if you're talking about polypropylene, okay, butyl rubber and all that, they have got 0.1. Yeah, they have got 0.1 watt per meter Kelvin. Others have got between 0.1 to 1 watt per meter Kelvin. Okay. So this is about thermal conductivity of materials. And what is the relevance of thermal conductivity in machine design? You have all seen the video, right? That disassembly assembly video I had shared in the first class. Hopefully all of you have seen it. What is the very important, why does thermal conductivity of materials play an important role in machine design? Why does thermal conductivity play an important role in machine design?
Because of rotation of the motors and other shafts and thermal, some heat is generated, so it may affect the material.
So, very good. So, one very important point to note is that all systems have certain losses within them. So, any machine that you take, what is one of the first specifications you would ask for? So, let us say you go to a market and you want to buy a grinder, okay, a mixer grinder for your house. What is the first specification you would ask of the product?
Power consumption.
The power consumption. Very good. So power consumption or the power rating is one of the most important parameters of any machine. So let us take the mixer grinder example. So what is the typical power rating of mixer grinders? Anybody with some interest in cooking? So mixer grinders, most common ones these days. How much? Most of them have about 500 watt to 1 kilowatt, okay, of power rating. So this is okay, power rating on the lower side. Now let us take fine, okay, and then what is the highest kind of power rating that you have encountered for, let us say, electrical systems?
Air conditioner.
That is still not very, no, air conditioner, the compressor power rating won't be very high.
Filament heaters.
Induction
So
motor.
filament
Induction
heaters,
heater.
these are all still 1-2 kilowatt, na? Like
Induction heater.
the highest power rating I have encountered is I don't know how many of you have heard. Raise your hand if you have heard about this Kaleshwaram lift irrigation project in Telangana. How many of you have heard about this project? Okay, so some of you have, most of you have not heard. It is a landmark project in the country because of the scale in which the water is being transported upstream, okay? And in this particular project, I don't know if you are, if you know what is lift irrigation. Basically what you do is you use water pump, submerged water pumps, to raise the level of water at a particular place, and then use canals which will use gravity to transport water from one place to another. This is called lift irrigation. You have to lift the water to a higher level at a spot to basically transport it upstream. And in this particular project, they have placed these pumps every 20 kilometers or something, and at each of these spots they are using pumps which are rated to the tune of some 600-700 megawatt, okay. That's a massive power rating of pumps. Now can you tell me something in hundreds of kilowatts motors which are rated in hundreds of kilowatts? So these days, if you take a look at the electric cars which are coming out, okay, so if you take either any of the Tesla cars or basically Tesla competitors, you would see that the power rating of the motor that they are using is in hundreds of HP. Okay, so they're basically somewhere around 100 kilowatts to maybe 300 kilowatts and so on. So means depending on what you are talking about, the power rating of the system may start from a few watts to even few hundred megawatts. Okay, now let's go back to the common product of mixer grinder. So if the mixer grinder is rated for 500 watt, okay, what do you think really is 500 watt? Is it the input power or the mechanical power output of the mixer grinder? What would be 500 watt?
Input power.
No, input power would not be 500 watt. That's not the usable power. Okay, it means I may give 1 kilowatt as input power, but if I don't have any output, then it's a useless machine, and that specification means nothing to me. So it is the output power. Okay, when it is basically what is of use to the end consumer. So if it is 500 watt at the output, what do you think might be the power at the input? What do you think might be the power at the input? So the system is going, there is going to be some efficiency in the system. What do you think might be a typical efficiency for motors?
80 to 90%.
80 to 90% is a typical efficiency, particularly for low powered things. As the power increases, normally efficiency also increases. Okay, so let's say 90%. So what does it mean? It means about 50 to 60 watt of heat is getting generated when you use the mixer grinder. Now, what happens to that heat which is getting generated? That heat will have to be released into the outer atmosphere. Okay. Uh, Now, if you cannot release it properly, if you cannot dissipate the heat properly, what will happen to the operating temperatures?
It will
It will
increase.
rise.
The operating temperatures will keep increasing. Okay, and if your system is very badly designed, then on the outside everything will look nice and good. Okay, if you touch the outer surface, it may not feel hot, but then the inner temperatures might be continuously rising because you are unable to dissipate the heat, and eventually something is going to break down, because every material that you use has got a certain operating temperature range. Okay, so thermal conductivity is very important in machine design, because ultimately whatever are the heat losses which are being generated in the system, and there will be heat losses, there is no question of no heat being generated. Okay, there will be heat losses, and you will have to dissipate this heat to the outside. So whatever materials you use, you got to ensure that there is a thermal pathway for the heat to go from wherever it is getting released to the ambient atmosphere. All right. Next, let us look at this modulus density plot. Okay. So on the y-axis over here, what you have is Young's modulus. So on the y-axis, we have Young's modulus. On the x-axis, you have density. Okay. Once again, what kind of a scale are we using? It is once again a logarithmic scale. Why do we have to use a logarithmic scale? Because the numbers that you are dealing with, okay, what are materials with some of the highest moduli? So some of the highest moduli for materials. So which material in this particular plot has got the highest modulus?
Tungsten carbide.
Tungsten carbide. Very good. So tungsten carbide has got the highest modulus. Which material has got the lowest modulus amongst these materials?
Flexible polymer.
So you either can look at this flexible polymer foam. Okay.
Polymer.
Yeah. So amongst this, flexible polymer foam has got the lowest modulus. What is the value of the highest modulus? Tungsten carbide. We looked at this yesterday. what is the value of this tungsten carbide modulus? It is about 400 GPa or 500 GPa, okay, in that particular range. What is the value of the modulus for the flexible foam? So if I just go here, what is the value here? Tempa minus 3 GPa is how much? 1 MPa, okay? So Tempa minus 4 GPa is how much? It is 100 kilopascals. So or 0.1 GPa. So this is 0.2, 0.3, 0.4, 0.5 0.5 MPa. Okay, so E here is about 0.5 MPa for this tungsten carbide. Okay, I don't recollect. So this one was fine. This one was how much? I think this was about 400 to 500.
GPA.
How much? 500. What did I say?
600 GPA, sir.
Okay, this is about 600 GPa. Okay, so this is the range of the elastic modulus that you are looking at. What is the range of density that you are looking at? So when it comes to flexible foams, what is the density of these flexible foams? So this is megagrams per meter cubed is basically 1000 grams per meter cubed. Okay, fine, doesn't matter. So let's talk in terms of kgs. Okay, so 1 means 1000 kg per meter cubed. How much is this? Flexible foam is how much? 0.01 means 10 kgs. So how much is it? 10, 20, 25. So when it comes to flexible foam, it is about 25 kg per meter cubed. This is the density of the flexible foams. What is the density of tungsten carbide? Density
15.
of actually highest value of density is not for tungsten carbide, it is for tungsten. Okay, so how much is it for tungsten? It is close to 20,000 kg per meter cube. So you can see the kind of range that you're dealing with. The most dense material is about 10,000 times denser than the lowest dense material amongst the engineering materials. And in terms of the modulus, the highest modulus that you have is about how much? Is about uh, 1 million times more stiff as compared to the lowest lowest modulus material. So there is a huge variation in terms of the modulus and the density of materials. Now if you ask the question, which material should I choose to get me a particular stiffness at the lowest weight? Okay, so because at the end of the day you don't really care either about the density or about the modulus. What you care is if you are going to make a panel or if you are going to use a beam, when they are subjected to a certain load, you want the deflection to be smaller than a certain value based on the stiffness constraint. Okay, so now what we are going to do is in these plots we will look at these lines. Okay, so you can see these lines over here, right? So see this line here, what do you think is this line? What I am just highlighting, what do you think is this line? On a log-log plot, when you draw a straight line, what does it correspond to? What do points on that line correspond to? What property will they have? So for
Linear.
points on this, so for points on this particular line, E by rho is constant. For points on this particular line, square root of E by rho is constant. For points on this particular line, cube root of E by rho is constant. Okay. Now, if I am looking at only a bar which is subjected to tension or compression, then to minimize the weight, what should I do? Should I minimize or maximize E by rho?
Maximize.
I have to maximize E by rho. Okay. So let us do one thing. I'm going to draw a line. I hope I can draw it properly. Okay, I have drawn this line. Now what I'm going to do is, as I move this line up, what am I doing? So for points on this line, at this point, E by rho is some value. If I move up, then E by rho is a higher value or a lower value?
Higher.
Higher value. Okay, so I want to see which one will give me, which would be a better choice. Okay, so now you can see. So if I have a bar and if I am going to subject it to tension or compression, is it better to make a bar out of flexible foam? These foams, or is it better to make it out of steels, metals?
Steels.
It is better to make it out of metals. Okay, and for that matter, even if I compare, okay, let me look at polymers. Okay, so I have a whole lot of polymers over here: polycarbonate, epoxy, PET, PEEK, polyester, and all. So amongst polymers and metals, which wins when it comes to weight reduction for bars subjected to tension or compression? Metals will win. Okay, because well, you can look at this curve. So metals lie on a curve uh, at a higher value. Okay, so this is the story for tension compression. And amongst the metals, you can see something very interesting. So if I put the line over here, which one wins, aluminium or steel alloys for weight reduction purposes?
Steel alloys.
No, steel is on the lower side of the line. Okay, so they're nearly the same. They're not very much different. Okay, and they're very much different. And in fact, ceramics happen to be the best choice from stiffness considerations. Okay, that is for tension or compression. Now, let me go to, I'll erase this. Let me go to panels, or let me draw the line for the beams. Okay, or let me go to panels directly. We don't have to that much time. So this curve over here, okay, is the one. This curve over here is the one on which, this line is the one on which all points are going to have the same value of cube root of E divided by rho. Now let us see how panels made of different materials will behave. First, let me look at foams. Okay, so if I take even the most flexible foam, all right, or even better, if I take rigid foam, so there are these polyurethane foams which are rigid. Okay, so what do I see? Which is a better choice for weight reduction? So consider three materials. Okay, so let us consider. So one, I am going to consider this rigid foam. Next, I am going to consider wood, and last I'm going to consider steels. Okay, so now tell me, amongst the three of them, rigid foam, wood, and steel, which would be a better choice for panels from weight reduction perspective, for a given
Rigid foam.
stiffness based on weight reduction perspective? So you can see this is the curve for steel. So you can see that wood and rigid foams are above this. So steel is actually a bad choice. Next, let me go to aluminium. So aluminium panels are a better choice than steel panels. Okay. Then let me move this even more up. Incidentally, wood is even better than aluminium. Okay. When it comes to weight reduction for panels, and rigid foam beats everything. Okay, it's a completely non-intuitive result that panels made out of foam can offer you, means for a given stiffness, panels made out of rigid foam will give you the lowest weight for a given stiffness requirement. Okay. All right. Next, we can do a similar kind of analysis for the beams also. Let me do this. Let it be there. For the beams, first I have to draw a line. Okay, so this is for the beams. Now let's go through this exercise. So you see, aluminum is a better choice for weight reduction. So now compared to wood, wood is slightly better than aluminum, and wood and rigid foam would offer similar weights. Okay, if you are looking at beams subjected to bending. Okay, so this is the Ashby chart for modulus and density. Next, let us look at the Ashby chart.
So,
Yeah.
so one thing is not clear, like when we are taking a constant, the line isn't passing through the origin. So how are we telling that E by rho ratio will be constant entire line?
No, why will it be passing through zero? Means we are taking
Sir, because the slope is not E by rho, so it will vary along the line also. Y by rho will vary.
no, just 1 second, okay? See, these are you are right. I have to see once. Okay, this is a log-log plot. So let us say square root of E by rho is constant. Okay, then what would happen? So if I take log of this,
would be
why would it be
ratio of
passing
log.
through origin? So what I will have is half times natural log of E will be equal to natural log of constant plus natural log of rho. Correct? So the slope of this particular curve, okay, y equals to, so what do I have? I have natural log of E equals to 2 times natural log of rho plus 2 times natural log of my constant. So it will not pass through origin. No? It will simply be a curve with slope 2. Y equals to mx plus c kind of a thing with m equals to 2. And the means the intercept will depend on the value of the constant. All right.
Okay, I got that. Yes, sir.
All right. Next, let us move on to this strength versus
Sir,
density.
I would like to interrupt for one moment. Sir, somebody is removing people from the meeting.
Hare Baba, who are these people? Okay, so what do I do?
So, what either someone of us can make everybody an attendee, or you can also do it. You're one of.
Why
Let,
don't you do that? If you can do it, can you do it?
so
Let me see. Actually, this attendee option, I'm not getting it. So this is, these are required attendees.
Just as I was speaking, somebody removed.
Just a second. Oma, lot of people are getting removed. Okay. Don't allow attendees to unmute, manage permissions.
So it is done now.
Okay, fine. Thank you. How do you do that? Can you tell me?
I didn't do it. I think somebody else did.
Okay, whoever has done it. Where does the option come to make everyone an attendee?
Sir, upper side there is a more action, then meeting details, and then meeting options in which you can select that who can present or not.
Yes, I have selected only I can present now. That is sufficient.
Yes, sir.
Okay. Okay, fine. I'll do that for every meeting. All right. Next, let us move on to this strength versus density thing. Okay, we'll just talk only a little bit over here. So once again, we can do this exercise of what is the lowest density we have already identified. That is about 25 kg per meter cubed. The lowest strength. Okay, the lowest strength. So if you look here, how much is this? So this is 0.1 MPa. This or 100 kilopascals, 10 kilopascals, 20, 30. So this is about 30 kilopascals. And if you look at the strength, okay, which has the highest strength, I guess this is tensile strength. Okay, they're not showing the compressive strength because ceramics have a smaller this thing. So in terms of the tensile strength, okay, which materials have got some of the highest tensile strengths? So you can see that CFRPs, okay, so CFRPs have got quite high tensile strength. Then you have ceramics, titanium alloys, steels, nickel alloys, all right, tungsten alloys. So all of these materials have got quite high strength, okay, and the highest strength is of the order of 1 to 2 GPa, okay. All right, now once again, now from strength perspective, if we again do this same exercise, okay, so if I'm looking at beams, so normally beams are the in yielding, this is what you typically bother about. So let me take this curve and then see who does a better job, okay. So now you can see that when it comes to the strength based requirements, who wins? So between foam and wood, which is a better choice from strength perspective? Between foam, okay, that is flexible foam, sorry, let me go to rigid foam, okay. So even between rigid foam and wood, which is a better choice for
Wood.
weight reduction? Actually,
Wood.
wood wins now, okay, for weight reduction. Now between steel alloys, okay, and aluminum alloys, okay. So if I put this in the middle of the steel thing, okay, So you can see that, okay, depending on the choice. So if you pick an appropriate choice of aluminum alloy, then you can actually get a lower strength for an aluminum structure as compared to a steel structure. Okay. For panels, once again, foam wins for the panels. So if I actually take a line with the slope for the panel, okay, I'm having trouble generating this slope. I don't know why. Okay, let me do this again. Okay, so now if I take this, then you can see that for the panels, interestingly, even foam panels are as good as carbon fiber reinforced panels uh, when you have a certain force and you're trying to decide things based on the weight which is going to be required in order to get that particular, means in order to meet the force requirement without any failure. And between aluminium and steel alloys, so aluminium is here, okay, you can see that aluminium alloys clearly win when it comes to designing panels keeping weight reduction in mind, even from strength perspective. Okay. All right. So I'm going to stop over here today. I'm going to share that form with a few questions. Just give me a minute. Any questions you can ask? All right. I have pasted it in the meeting chat, the form. You can start filling it up.
Sir, when one line passes through like multiple materials, like all are similar, like in comparison, right? Those
Yes, that's what it means. So
and
from
those
weight
lying
perspective,
above the line, like suppose towards the left upper corner, they are better.
yes, materials which are lying above the line would give you lower weight.
Yes.
See, over here we are only considering things from weight perspective, but in many applications, space may also be a big constraint. Okay, so it may so happen that with large enough space, rigid foam is a better option. But if you do not have enough space, something else may be better. So just keep that in mind. ಹಲೋ. ಹಾ ಪ್ರಸ್ತುತ ಮಂತ್ರಿ. I will be talking a little bit about this traction slip characteristics, mainly the experimental observations under different conditions. And then I'll talk a little bit about determining the contact stresses and on effect of this track irregularities on contact load, and finally on that estimation of that contact patch using this strips method, and estimation of shear stresses using the FA strip method or something. Experimentally, the traction slip characteristic. Yeah, the right. Okay. Okay. Sure. Okay. Okay. So you will be when is this starting? 4 or 4:30? 4 o'clock. Okay. So you will be giving from 4. Acha. Okay. Yeah, that's what it says. It wasn't very clear what is going on, but yeah. It is very confusing because there is no brochure, agenda, timetable, nothing. So we only have cryptic emails with cryptic titles. Uh-huh. Achha, okay. 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 Okay, I am also not going to get too deep. Means it is more about nothing too much about maths, but just giving some basic idea about different things. Uh, Yeah. I'll request at least Professor Dev to ask somebody to make a small brochure with our names so that later on, when I'm writing something, I can say, okay, I gave a seminar. At least one. Oh no, I don't. This one is not looking formal at all. It looks so informal. This whole thing. Yes, there is nothing. This is more like general chat across the internet. So. Hmm. ठीक है. Yeah. It's fine. Okay. हाँ. हाँ. Okay, fine. Thanks. Very good. Register ಅಂದ್ರೆ.
Excuse me, sir.
Yeah.
Sir, yesterday I attended the full 2 hour class, but I wasn't able to open the form. So, like I tried 2 3 times to submit my form, but it didn't happen. And later, when I tried after 10 or 15 minutes, it said that the form isn't accepting any more requests. So, will you like still give me an attendance, or you can check in the MS Teams. I've attended it for the 2 hours.
One second. This is January. Today is Thursday, January 11th. No, talking about.
So
Okay,
yesterday,
we'll
13th.
13th. Okay, just a second. Yeah. Okay. Okay, can you do one thing? I'm going to open it now. Do you have a class now?
No, sir.
Hello?
No, sir.
Okay, so if you don't have a class, I'm just opening it now.
Okay.
Okay, I have opened this. I'll share the link again.
Thank you, sir.
I'm going to paste it. I will say Jan 13 link. Okay, I have pasted it. You can do it.
Thank you, sir.
Yeah.